All right, so we're continuing our discussion of an atomistic view of the term diffusivity, which we defined as alpha times omega times lambda squared. And in the previous video, we looked at the omega term and we looked at nu, which was our frequency or probability of having the energy to make the jump. And so in this video, we're going to talk about lambda, which is our probability of that site being vacant. So the site we're trying to jump into. All right. So the probability of a site being vacant depends on the species that we're looking at. So in this way, we kind of want to define what type of diffusivity or diffusion we're actually looking at, right? So one way we can actually look at diffusion of atoms or ions themselves. And we can also look at diffusion in terms of the defect or vacancy, right? So we can also look at them as the defect or vacancy diffusing, right? So we're basically looking at an empty site moving, right? So we're basically looking at the opposite of atoms and ions. And so those are the kind of the two ways that we can look at it. So what I want you to do to get started is we're going to work an example of what you think these probabilities might be. So let me switch over to the slide so it's a little easier for you to see that, and we will discuss. All right. So here's the question I want you to answer before we get too much into this. And so I'll give you the instructions here and then go over the quiz, fill that out, and come back and we will discuss your responses. So what I want you to do is we've just talked about theta, this probability of a site being vacant, and it depends on the species that we're actually talking about. So what I want you to do is I want you to come up with an estimate of what you think the value of theta will be for each of the following diffusing species. So think about theta for a vacancy, theta for an interstitial site or interstitial atom, and theta for an atom/ion. So see if you can just come up with an estimate, best guess of those three, and then come back and we will talk more about this theta term. All right, so let's now see if we can come up with what we think the probabilities are for the various species. And so I'm just going to sketch a simple structure that we can use to talk about this. So don't mind if it's kind of sloppy here, but we have a vacancy here. We can talk about an interstitial, and then we can also talk about an atom, right? So if we're talking about defect diffusivity, right? So this would be vacancies or interstitials. Then what we see is that if we look at, let's first look at this interstitial, right? An interstitial is located here in the space between. And if we look at all of the other interstitial sites around it, which is where this would hop to, right? So it would either go here or here or here into one of these spots, sorry. So one of those, right? It's going to go somewhere into an adjacent interstitial. Well, there tends to not be other atoms in those locations, right? There tends to be a lot of interstitials and not a lot of things in there. And so the concentration of that's occupied is low. So for interstitials, the concentration of occupied interstitials is low. So what that means is that the probability of that site being empty, right, is basically almost 100%, right? So we can approximate that as 1, right? Because this is basically the probability, so the maximum is 1. And so almost all these adjacent sites are empty, and so it can jump into any one of those, and so we have a value of 1. All right, so let's think about it from the vacancy point of view then. So for a vacancy, and I've kind of covered it up here, but this one here, right? Typically, and we've done some calculations and thought about vacancies, right? Too many vacancies would sort of destabilize the structure. And if we look at the thermally activated process, we predict a fairly small number of vacancies. So if we look at it from the vacancy point of view, this is our diffusing species. So it can either move here, 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 right? Any of the adjacent species, or even over here too. I haven't exactly drawn a good structure there, but any adjacent one. And again, since there tends to be a low amount of vacancies, it's the probability of any of these sites being an atom that can switch places and not another vacancy is pretty high, right? So the probability here is also close to 1, because it can these sites are available, and by available I mean that they're an atom, and that atom can move into the vacancy, and the vacancy can move into its position, right? So then that means that it is also close to 1. So lastly, if we're talking about atoms and ions, right? So now let me draw this again, because it's getting kind of cluttered. All right, so now if we look at a typical atom, say this one, right? And maybe I should draw more around it. Again, we go by the same kind of idea here, is that we know the vacancy concentration is relatively low. And so the probability that an atom will have a vacancy near it is also pretty low, right? So these atoms around the vacancy all have a probability, but this one over here doesn't, right? And that's pretty common because we're talking about fairly small percentages of vacancies that an atom can hop into. So this probability, and I'll just call this atom, is basically close to 0, right? It's not obviously 0, but it's closer to 0 than it is to 1. So it's a really small number, however you want to write that, but essentially it's close to 1. And so that's what we get when we look at these probabilities, is that we have, we basically have very high numbers, high probabilities if we talk about interstitials and vacancies, but if we're talking about it from the point of view of an atom, it tends to be pretty low. Again, not 0, but closer to 0 than closer to 1. And again, this probability would obviously change with the higher fraction of vacancies that we have in a given material. All right, so this is, again, another way to write this might be much lower than 1.